Hi, I'd like to give a little bit of an addendum on the resonant system and the frequencies that we were looking at in this last setup. So there's a few different frequencies that we had. Omega naught root k over m is the natural frequency. This is what frequency it would have if there was no damping. With damping, things get a little bit complicated. So we found a couple of different frequencies. We found this omega d, and in the notes we actually found a different one, omega max. So let me explain what these things are. Omega d is the frequency that the system will naturally respond at in the transient response when there's damping. So when you work out, okay, we've got some, like let's say omega naught is 10 and it had some initial position, has some damping, and you let it go. There's a transient response which has this exponential decay, and this will be at the frequency of omega d. So we can see this by doing some example. We put in the ODE and give it some driving force, and then you can work out what omega d is. And in this particular case, for this zeta and this omega naught, the damped natural frequency is 9.98. And that's exactly the response of the transient terms, right? But that's not the response that that's not the response of the steady state term. The steady state term is at whatever amplitude we drive it at. So here's three different versions of this solution where you drive it at the natural frequency, omega naught, where you drive it at the damped frequency, and when you drive it at this different one, omega max, which is actually the true resonant frequency when there's damping. Okay, so you can see that the amplitude is different. It's a little bit hard to tell, but when we drive it at the natural frequency, we get an amplitude of 8. There's an 8 in front of the steady state coast term, the one without the exponential decay. When you drive it at omega d, so we put in omega d is omega naught root 1 minus zeta squared. That's from the work that we did with omega d. Where that came from is we solved the system analytically, and we found out that the transient terms occur at this frequency. Then when we defined zeta and omega naught, we were able to rewrite that in terms of, well, it's not in the coast term actually, it's in the underdamped term, this one, yes. We were able to rewrite that as omega naught root 1 minus zeta squared by making this definition and this definition. Okay, so if you put in that as the driving frequency, you have a different amplitude. So there we have this much coast term and this much sine term. Now you can already tell that this is at a larger amplitude overall than the natural frequency gave us. But to find out exactly what amplitude it's at, we've got to take the root of the sum of the square of those terms. So let's do that down here. The root of the sum of the square of this term and this term will give us 8.01. So it's slightly higher for this zeta than we would have gotten if we drove it at the natural frequency. As zeta gets smaller, this is, well, first of all, the damped frequency, the damped natural frequency, omega d, is going to get closer and closer to just omega naught. And then when we drive it at that frequency, the amplitude is going to get closer and closer to the amplitude at the natural frequency. Okay, still, that's not the maximum amplitude we could get. If instead we put in this omega max term, then we find that the amplitude, this -8 and 0.5 in sine, -8 cos and 0.5 in sine, turns out to be slightly larger. So larger still than we got at omega d. All right, but why? How did we know that we should get a larger response at omega naught root 1 minus 2 zeta squared? What's with this 2? Where'd that come from? Well, remember when we worked out the amplitude should be this? Here it is written in quality factor. You could have had it in the zeta form instead. We can find out where the real max of this is by figuring out where the denominator is at a minimum. And the denominator is going to be at a minimum when the thing under the root is at a minimum. And to find out where this is at a minimum, like what frequency, we can take a derivative of it with respect to frequency. But if we find out the minimum, or rather the frequency squared that gives a max, that will also tell us the frequency. So let's instead differentiate with respect to omega squared. Pretend that that's the variable instead. So the reason we do that is because that's an easier derivative and easier to solve. So now we can rearrange, get omega squared is equal to this, and then omega max equals the root of that, which is omega naught root 1 minus 1 over 2 q squared. The Q, remember, is 1 over 2 zeta. So when we substitute that in, that's where we get this 1 over Q squared will be a 4 zeta squared. The 4 cancels with one of the 2's and the 4 cancels with this one, and we get root 1 minus zeta squared as the actual maximum response resonant frequency. If zeta is small, these all become really close together, and the response becomes really close together as well. So we can check this out. I encourage you to try a few examples of this. Let's give it a shot here. How about we make zeta equal to a quarter and see if we can get some big differences there. So when zeta is equal to a quarter, now the frequency that omega max occurs at, the frequency where we get the most response, the resonant frequency, is different by a fair bit, and the response will be a fair bit larger now. So let's check. The natural response is 2. The response at the damped natural frequency, which is 9.68, and you can see that in every case is the transient term's response frequency. If we drive it at that frequency, then we get this slightly larger amplitude. Let's check. Square root of Control C, Control V, that thing squared, plus, select that, Control C, Control V, and that'll be 2.04. Okay, and that'll be smaller than what we'll get at the omega max. Yeah, let's see. That squared plus this thing squared. Aha, so the one at omega max is even larger. What about if we go to a very small zeta? So what about 1 over 40? Okay, now the frequencies are incredibly close together, so we might be even running into the limits of precision soon if we take this too far. Let's have a look. So the natural frequency, this first term here, makes it respond at an amplitude of 20. With lower damping, notice that we're going up in the response amplitude here. So yeah, we weren't actually changing the driving force with the damping here. So this is real. This is just like an increase in the amplitude by decreasing the damping, leaving everything else the same. So what happens if we drive it at the damped natural frequency? That's this second term here, where we get root of this thing squared plus this squared. And that one responds at a slightly higher amplitude than 20. Very small change now. And then the third frequency, the actual resonant frequency, of not 10 rads per second, but 9.993748045 rads per second. This one gives us not 20, but 20.006, slightly higher. So for decent quality factors, remember that Q is 1 over 2 times zeta. So here we're at a quality factor of 20. For decent quality factors, like if you have a quality factor that's 50 or 100, then in a lot of situations you're going to have a difficult time doing experimental measures that see much difference between these kind of amplitudes. So that's why in a lot of situations you'll just end up saying that this thing is the resonant frequency and not worrying about the fact that the true resonant frequency is slightly lower. All right, another thing to talk about, now that I've got your attention and I'm making another video anyway, we may as well talk a little bit about nonlinear damping. So all of the analytical work we've done so far had linear damping. This is when we have a damping force that's proportional to the velocity to the power of 1. And that actually is responsible for reaching this steady state amplitude. If it wasn't for why does it level off, right? As you add in more and more energy from the driving force, then the velocity eventually gets large enough that this damping is able to remove the extra energy that's added each cycle. So it doesn't build up anymore. You reach a steady state amplitude where the added energy from the driving force each cycle balances out with the energy that's been dissipated by the damping. That actually was hinted at, of course, by this definition of quality factor being 2 pi peak energy stored over energy dissipated per cycle. The amount that it's going to oscillate above its natural, its kind of response at low frequency when you're at resonance is the peak energy stored times 2 pi ratio to the energy dissipated per cycle. It's when we are directly balancing the extra energy that we're adding with the energy that we're dissipating each cycle. Now, for this to work, you need this linear damping. You need a damping where the added velocity from having the thing have a larger amplitude leads to more damping force that's going to be dissipating more energy in a way that's more than proportional to the extra amplitude, right? So this way the energy can eventually level off and we settle it out. It doesn't increase amplitude forever. But that's not the case when we have something like this ground friction resonator. So this has a friction force, which is just a constant. It's constant as long as it's moving in a certain direction. So this gave us some interesting results where for a low enough friction force that it even moves at all, there is no steady state amplitude. It will just build up continuously as we add more and more energy every cycle and never really level off, never come to a stop. This is an example of nonlinear damping, like constant damping, rather than one that's proportional to velocity. On the other side of it, we had nonlinear damping and something like this space station module question, where the damping is now proportional to velocity squared. In this setup, you can have some more interesting, some additional interesting effects that show up, especially because of this damping being proportional to velocity squared. So back in the example of resonant frequency here, why do you think it is that the damping, that with damping, the frequency where it responds the most, where it has the maximum amplitude, is slightly below the resonance? Well, the reason is that when it's moving back and forth, like what's the difference between below and above resonance? Above resonance, it's moving back and forth slightly faster, right? It has more velocity. Below resonance, it's moving back and forth slightly slower. If the amplitude is the same, then we would have more energy lost when we're just above resonant frequency, just above omega naught, let's say, than when we're just below omega naught. So when you're just above omega naught, you'd have more energy lost to damping than you would just below. And that's why the max amplitude is not at the natural frequency, but just slightly below it. You have more amplitude there because there's less energy lost to damping, because the velocity is lower, not due to a smaller position amplitude, but because the frequency is lower. So with that in mind, if we have a system where now there's nonlinear damping, where it goes like velocity squared instead, you can have a couple of extra things showing up. For one, you would expect that the real frequency where it responds the most is even more below the natural frequency, right? If we are more strongly velocity dependent than we were earlier, then we should be even lower than the natural frequency, where then the frequency that will give us the most amplitude should be even lower than the natural frequency compared to what it was in linear damping. In addition to that, the way that the amplitude depends on the driving force will not be the same anymore. It used to be in linear damping that if you double the driving force, you double the amplitude. Now, though, doubling the amplitude would mean quadrupling the damping force. So just doubling the driving force won't keep up with that. And you'd find that the amplitude no longer behaves linearly with the driving force like it does for nonlinear damping. So these are some interesting, really difficult effects of nonlinear damping things and ways that you can use the understanding and thinking about this linear case to extend to even more complicated problems.